Topic for this video is gas laws. The essential questions are: what are the postulates of kinetic molecular theory? How does kinetic energy relate to temperature? How does a gas's quantity, volume, or temperature affect its pressure? And what is an ideal gas? So kinetic molecular theory is a description of gas particles, how they behave. Okay, so there's a couple postulates that we're assuming is true. The first is that gas molecules are small particles and they travel in straight lines, and they're going to undergo elastic collisions, which means they're going to run into each other or they're going to run into the walls of the container. And that's the only way they end up changing direction, is by colliding with something. The elastic part in the collisions means that there's not going to lose any energy. Okay, so they're going to continue on with the same amount of kinetic energy as they had before. The next part is that kinetic energy of the molecules is going to be proportional to temperature, so that means when the kinetic energy goes up, the temperature is going to go up. And then the last part assumes that the gas molecules have no volume. Okay, they're essentially tiny, 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 and that there's no attractive forces between them, so their motion would be random then. So, temperature is a measure of the average kinetic energy of particles. The units we use in science are degrees Celsius or degrees Kelvin. We do not use Fahrenheit in scientific settings. So what this basically says is that if you have a cooler gas, it's going to have fewer and less energetic collisions. If you have a hotter gas, it's going to be more energetic, so they'll have more collisions. So this is showing you where water boils and freezes on all three temperature scales. We're going to focus again on Celsius and Kelvin. So water freezes at 0 degrees Celsius, which is 273 degrees Kelvin, and water boils at 100 degrees Celsius, which is 373 degrees Kelvin. So Kelvin, to find it, you just take Celsius and add 273. That's it. So if we have room temperature of 25 degrees Celsius, we want to find Kelvin, we just add 273 and we get 298 Kelvin. If we have liquid nitrogen at negative 196 degrees Celsius, we add 273 and we get 77 Kelvin. Down at the bottom, you'll see this absolute zero thing. And what that is the lowest temperature possible, and it's where particles have no kinetic energy. Particles even continue vibrating a little bit until they get to absolute zero, and then they stop moving. So that's 0 Kelvin. So now we're going to talk about pressure. Pressure is a force caused by gas molecules colliding with the container walls. So there's a couple ways to measure pressure. One is with a manometer, and the other is a barometer. So those are tools that we use to measure air pressure a lot of the time. Okay, and so we have several different units we can use for pressure, and the units are listed below with their equivalencies. So 1 atmosphere is equal to 760 millimeters of mercury. That's equal to 760 torr, and that's equal to 101.3 kilopascals. Okay, so all of those are the air pressure at sea level. So let's look at some factors that affect the pressure of a gas. The first is the amount of the gas, which more gas means that there's more particles in that space, and more particles mean that there's going to have more collisions, and collisions is what creates pressure. So we can deduce that if we have more gas, we're going to have a higher pressure. The volume of a gas is the next one. If there's more space for the gas, that's going to mean the particles have more room and they're going to collide less. So more volume is going to be a lower pressure. The next one is the temperature of a gas. More temperature means more kinetic energy, and that in turn means the particles are moving faster, and that means more collisions. So higher temperature is going to equal a higher pressure. So an ideal gas is one that perfectly obeys the kinetic molecular theory and gas laws. A gas is most likely to behave like an ideal gas if it's a small or lightweight molecular atom like hydrogen or helium. It's also most likely to behave like an ideal gas if the temperature is high and the pressure is low. These conditions will keep gas particles spread the furthest apart that they can be. But a real gas, so in the real world, these are going to deviate from ideal gas behavior. So this happens when a gas is made up of large heavy molecules like SO3, sulfur trioxide, or when the temperature is low or when the pressure is high. Okay, so here's a diagram showing you how ideal gases behave and what happens with real gases. And it's showing that the volume of a gas is really small compared to the volume area on an ideal gas, but in real gases sometimes the volume is really small also, so the volume that the gas is taking is significant in those cases. Okay, and this is also showing you at low pressure they're able to move about like they should. At high pressure they're kind of contained, and so that can create some deviations from an ideal gas. And the molecules are closer together in that situation also.